My name is Varun, and I'll be presenting our work on a meta-heuristic that we propose for network slicing under traffic uncertainty. So the problem arises in the context of 5G networks, wherein a network operator, given a physical substrate network infrastructure, can host multiple networks, one on top of the other. This concept is called network slicing because the network operator is able to slice part of his resources and allocate to these logical networks. So here in this picture, we have a graph that is composed of nodes and edges, which is a physical network. And this belongs to the network operator. And then you have a network slice request that is coming from a tenant, which could be a railway operator or somebody who wants to set up a network in a conference, etc. He requests for a network slice to be set up on top of the infrastructure between nodes A to D and A to C, wherein a demand of volume D has to be routed between functions which are very specific to the service that the tenant is requesting. So the outcome of solving the problem would be the picture on the right side, where we see that a network slice has been hosted on the physical network infrastructure. The virtual network functions have been located on node B, and then the traffic is routed from A to D through node B and A to C through node B. So this is the outcome of solving the problem. But bear in mind that the traffic in next generation networks would be heavily dynamic, so we have to consider the uncertain nature of it as well. So we modeled this problem as a mathematical model. We considered a graph to be composed of nodes V and edges C. In reality, they are data centers connected by optical fiber cables. They have residual capacities. Their capacities, when deemed insufficient, can also be expanded. And we also consider utilization costs and one-time capacity installation costs as well. So as to the network slice that is coming from the tenant, we assume that the network slice is composed of a set of point-to-point demands, and an uncertain traffic flow is to be routed from source S to T through a sequence of network functions that are specific to the service that the tenant requests. So to model the problem, we consider 4 families of variables. The first variable indicates the fraction of the demand that is routed through an arc, which is a routing variable. The other 3 variables indicate the capacity modules that are assigned to the virtual functions, the capacity modules that are installed on the nodes and the edges. And the objective of the problem would be to minimize the worst case cumulative costs of substrate resource utilization and potential capacity expansions to host this particular network slice. Here we have the mathematical model of the robust network slice design problem. As we said earlier, the objective is to minimize the costs. The problem consists of multi-commodity flow constraints, which you can see over here, typical multi-commodity flow constraints. And then you have capacity constraints on the virtual network functions that take into consideration the uncertainty as well. As you can see, it considers all the traffic matrices that are available. And then you have capacity constraints on the nodes which are hosting the virtual network functions, capacity constraints on the edges through which the uncertain traffic demand is being routed. Finally, we have the decision variables. Before we move on to the next slide, I'd like to remark that this problem considers an exhaustive number of traffic matrices, which is prohibitively large to be used in a problem. So the computational complexity increases very much. So one way to circumvent this would be to define the traffic coefficient to belong to an uncertainty set, which is modeled along the lines of a multiband uncertainty model. So the uncertain traffic coefficient is assumed to belong to an interval, and this interval is partitioned into multiple bands, and a histogram is basically constructed, which depicts the distribution of the traffic coefficients. So once you have the histogram of the traffic coefficients, as you can see on the left side of the figure that is depicted over here for a normal distribution, we can impose an upper and lower limit on the number of coefficients that deviate in each and every band, and then solve the problem for the worst case realization of the coefficients, obeying this particular multiband uncertainty set. So what we can do is revisit the problem that we proposed earlier and derive a compact reformulation having described the behavior of the uncertain coefficient using the uncertainty set. So this is the problem that we have in hand. We tried to solve this problem using Cplex, but the results were often very bad. We used an off-the-shelf service called IBM's Decision Optimization on cloud, which yielded very negligible improvements in the range of 0 to 3%. So we used an existing heuristic called the maximum ant system, which is embedded in a hypercube framework to solve a problem. So in the heuristic, we have an inner loop wherein a set of computing agents incrementally construct feasible solutions to our robust network slice descent problem in the inner loop, whereas the outer loop repeats this process until a certain time limit is reached while updating the pheromone trails based on the quality of the solutions that are generated by the computing agents. So this is the pseudocode of the meta-heuristic that we propose. We feed a problem instance and a parameter file, and then as an output, we expect a feasible solution to the robust NSCP. So we initialize the values of the pheromone trails to 0.5, and while a time limit is not exceeded, we allow a set of ants, in this case, psi number of ants, to construct a feasible solution to the robust NSCP. So what the ants do is select a combination of paths for each and every demand, and then once the routing paths are established for each and every demand, you can fix the remaining variables and derive the capacity that is required to support this particular routing. So after this, we can derive a feasible solution to the robust NSDP, compute the cost of the solution, and then depending on once all the ants finish computing the feasible solutions to the NSDP, we can update the pheromone trails according to the pheromone reinforcement model and the quality of the solutions that are being generated. So this process continues until a time limit until a global time limit is reached. This sums up the heuristic that we've actually proposed for the robust NSDP. I'm not getting into much details of it. You can find it in the paper. So moving on to the computational results, the environment that we considered to solve the problem was JUMP, which was used to model the ILP formulation, and Cplex was used to solve these ILP models. And then a 1 hour time limit was imposed for each of these instances. We considered 10 network topologies from SNDlib, and the node capacity and the edge capacities are set according to previous research works that are available in the paper. You can check it out for more details. So are the details for the network slice as well. So for the parameter configuration, we assumed a population size of 6 computing agents plus 3 elitist agents, which are tasked with constructing the feasible solutions to the robust NSDP. The 3 elitist agents construct greedy solutions to the robust NSDP in intervals for every 50 iterations of the ant-calling optimization heuristic. The pheromone rate is set to 0.1, and we consider a truncated time limit of 2400 per instance for the meta-heuristic. So the performance profile captures the performance of the proposed solution methods over here. One was Cplex, which is used to solve the mathematical model. The other is the ACO-based meta-heuristic that we propose. The third one is a greedy heuristic, which basically routes the demands over the shortest paths and then designs a network slice. So what we can see from the performance profile is that the probability ACO outperforms the remaining solution methods with a probability of 0.97. Whereas the probability of a Cplex to return solutions of improved optimality gap is just 0.03, which is just one instance out of the 30 that we actually consider. So as you relax the performance requirements, you can see that the number of instances for which ACO is able to provide better solutions increases to 97%. Whereas you can see for Cplex, it doesn't increase much, even though you increase the performance ratio to be within a factor of 10 of the best performing solution method. Greedy heuristic is able to perform reasonably well, but ultimately ant colony optimization heuristic is the best performing solution method, not only quantitatively but also qualitatively as well, as we observed for some instances. ACO was able to provide improvements in the order of uh, um, uh, in the magnitude of order of 10, whereas the other heuristics, the greedy heuristic was able to catch up with it, but not exactly provide the best solutions. So, to sum up, what we did was we proposed multi-band robust NSTP, which can design a network slice to provide robustness guarantees against traffic uncertainties. The inclusion of these constraints, robust constraints, led to challenging problem instances. So we proposed an ACO-based meta-heuristic, which yielded improved solutions for 97% of the considered problem instances, whereas Cplex was able to return improved solutions for just 3% of the instances. So consequently, the solutions from the heuristic also offered us promising cost savings while also preserving robustness, as we depicted in the performance profile. With this, I'd like to conclude my presentation, and thank you very much.